All right, so today in our video, we are going to learn about the basics of work. All right, we'll talk a little bit about what work is, but honestly, that'll come in a later video. Really today, I want to focus on making sure that you understand, how/when a force does work. And really the main focus of this is going to be learning how to calculate that work. How do we calculate how much work is done by a force? Okay, so that's going to be the main focus today. All right, so here we go. So first of all, a couple quick things about work. So this is, like I said, just kind of a general overview. We'll learn more about this in a later video. But for now, basically what you need to know is this. That work, when you do work on an object, you're changing the object's energy in some way. So that means that at least one portion of the object's total energy is going to change. All right, and in order for that to happen, in order for your energy to change, there has to be a force doing work. All right. Now, in order for a force to do work, here's what needs to happen. In order for a force to do work on an object, the first condition is the object has to be moving. If the object is not moving, no matter what, no work is being done. All right. So if you stand holding a 100-pound dumbbell over your head all day long as you're holding it there and not moving it, you are not doing work because you are not changing the energy in any way, shape, or form, because you're not changing any component of this equation. All right. And then number two, this is the one that's a little bit weird. The direction of the motion can't be perpendicular to the direction of the force. Okay. So if your object is moving this way, if the displacement vector is this way, and the force vector is this way, that is no work being done. Because that force there is not affecting the motion. Okay. All right. Now, let's talk about signs. All right. The amount of work that a force does is positive if the force is working with the object's motion, if the force is somehow contributing to the motion. All right. And the work is negative if the force is working against the object's motion. Okay, and that gives further explanation for why this is zero, right? Because that force is neither working with nor against that horizontal motion. All right. Like I said, when we get to a later video, we're going to focus on a little bit more on sort of how the different types of work that can be done. All right. And in doing so, we'll talk about the fact that there are two different types of forces. All right. There are conservative forces. And there are what are called non-conservative forces, all right? So it turns out that if a conservative force does work, all it's doing is converting energy to or from potential energy, okay? So when you drop an object, gravity does work, but all of that work of gravity is doing is it's converting gravitational potential energy to kinetic energy, okay? Conversely, when you throw an object up into the air, as it's going up, gravity converts the KE back into potential energy, okay? So, long story short, conservative forces don't change the total energy. They just cause the energy to change from one form to another. All right, so again, that's kind of a preview of things to come. All right, non-conservative forces tend to be more important in terms of work. Because a non-conservative force will change the object's total energy, okay? When you lift an object, you are a non-conservative force, or you're exerting a non-conservative force, and so you're transferring energy from one object, from you, to the other object, okay? And so if you're doing positive work, you're increasing the total energy. If you're doing negative work, you're decreasing the total energy, okay? So a lot of this is probably like, oh, what's he talking about? I get it. There's a lot of information here, but I wanted to kind of throw it at you now so you can kind of stew on it a little bit. And then by the time we get to the video where we actually have to use all of this information, you'll have had a little bit of time to think about it. And hopefully as you're solving some of the problems on this first worksheet, you can kind of be thinking a little bit about how is the work changing my energy, okay? So that's a little bit in the background of this, kind of what you're going to be doing in this video and on the associated assignments. All right, so let's talk. This is sort of the, if I lost you, pause, take a deep breath, this is really what you need to know, okay? So remember, work is done by a force, all right? So when you calculate work, you're actually taking what's called a dot product, all right? And this is some math that most of you probably haven't learned at this point. So when you calculate work, what you're doing is you're multiplying two vectors, and those two vectors are a force vector and a displacement vector. And in mathematics, it actually turns out there are two ways you can multiply vectors. All right, when you calculate work, you're using what's called a dot product, sometimes called a scalar product. So this little dot here is a symbol for a type of vector multiplication most of you haven't learned about. Okay, it's called a dot product or a scalar product. All right. So to calculate it, there are basically three ways that you can do it. All right. So to calculate work, option number one, multiply the magnitude of the force by the magnitude of the displacement, and multiply that by the cosine of the angle between those two vectors. Okay, this is huge. All right, so F is the magnitude of the force. Delta X is the displacement vector, but again, just the magnitude. I wish I had written that there. All right, and theta, this is the piece people always screw up. It's the angle between the force and the displacement vectors. All right, so if your object is moving this way and your force is, I don't know, maybe somebody's pushing it backwards trying to stop it. All right, then this is what your angle would be. Okay? All right, so that is one way to calculate work. All right. The second way to do it is, let me clean up the board here a little bit. The second way to do it is to split your force up into components. Split your force up into components. And what you're going to do is you're going to look for the component of the force that is parallel to the displacement. So this F parallel is the magnitude of the force in the direction of the displacement. Maybe I should say parallel to the displacement. Okay? So split your force up into components, find the component of the force that's parallel to the displacement, and then multiply. All right? And then the third option is the opposite. Instead of splitting your force into components, you're going to split your displacement into components. And again, what you want is the component of the displacement that is parallel to the force, and then multiply. All right? So, which of these methods works best? So I wanted to show you all of these. Because if you go out and take a college physics class, my guess is your professor will probably just give you this and say, there you go, solve it. But after a lot of deliberation and whatnot, so I used to work really hard to make sure my students understood all three of these methods. But I've realized that I think that's a battle not worth having, largely because more often than not, you need to make a free body diagram to solve the problems anyway. And when you make your free body diagram, you're going to split your forces up into components. So this guy right here is our jam. So this is how we're going to solve our work problems, is by using that. All right. Now, when we take, if you do move on and take AP, we'll use these other two guys a little bit. But again, really, more often than not, this one is just as effective. Okay. I should note they do all give you the same answer. All right, anyway, I am rambling. Let's go on and do this. So this little paragraph down here basically says what I just said. So to solve work problems, you're going to make a free body diagram and then use this guy. All right. I guess I should comment, when you use this, you got to watch your signs. Okay. If you're, parallel component of your force and your displacement are in opposite directions, then you need to make a note of that. All right, so I have talked too much. Let's do 3 or 4 examples, all right? And the examples are going to be pretty quick. All right, so example number 1, you've got a force parallel to the displacement, all right? So what if we had something like this? What if we have a box just sitting here and Roy decides he's going to push it? Okay, so let's come up with some numbers here. Let's suppose it's a 10-kilogram box. All right, he's going to push it with a force of, I don't know, how about 50 newtons. All right, let's calculate the work done while the box slides. Sorry. Let's calculate the work that Roy does while the box slides through a distance of 20 meters. Okay, so what I just said brings up an important point. When you calculate the work, you're calculating the work done by a force. All right, so in this instance, we are calculating the work that Roy did. All right, and so in order to do that, what we're going to do is we are going to calculate the force that Roy is exerting parallel to the displacement and multiply it by that displacement. Okay, so in this one, you really don't even need to make a free body diagram, right? Because all that's happening is Roy is pushing forwards. Here's our force of Roy. It's 50 newtons. Okay, so what I want to do is I need to now think, all right, what direction is my displacement? That way. What direction is my force? What component of the force is parallel to the displacement? All of it. So here, I'm literally just going to multiply. All right, so I'm going to take my force of Roy, 50 newtons. I'm going to multiply it by the displacement, 20 meters. That gives you the 1,000. The units there are Newton meters, which if you go back to our energy notes and figure this out, you will discover that that is the same as 1,000 joules. All right, so there we go. That's all there is to that one. If the force and displacement are parallel, you just multiply your force by your displacement. Okay. All right, example number 2. What if instead the box is sliding towards Roy? Okay, so still 10 kilograms, and Roy decides he wants to stop it. All right, so now what's going to happen is here's Roy's force. What did I have before? 50 newtons. All right. Let's suppose that it slides this way through a displacement of 50 meters. Oh, sorry, 20 meters is what I did before. We'll use the same numbers. 20 meters. And let's calculate the work done by Roy. So work done by Roy is force of Roy parallel times the displacement. So once again, the forces are parallel. Technically, they're anti-parallel, right? Because they, anti-parallel just means they're parallel, but they point in opposite directions, right? So our force is this way, our displacement is that way. So that's what anti-parallel means. Okay, so again, we just multiply, but you've got to watch your signs, all right? And the thing to notice here is in this instance, my displacement is negative because the box is sliding to the left, okay? So I'm going to simply multiply 50 newtons worth of force times negative 20 meters worth of displacement gives me negative 1,000 joules. All right, so remember, anytime your force opposes your motion, you're going to have negative work. All right, in that previous example, the force was contributing to the motion, so we had positive work. All right, so what about if the force is perpendicular to the displacement? Well, in either of those examples, here's my box, 10 kilograms. Let's say it's sliding along this way still. This time, let's calculate the work done by gravity. All right, so let's think about what's happening here. You know what? Let's have it sliding along. Okay, let's do this. It's sliding along this way. Okay, let's say that it goes through a displacement, again, of negative 20 meters. All right, and let's suppose it's frictionless. In this particular example, let's suppose it's frictionless. All right. And let's calculate the work done by both gravity and the normal force. So when I started this, I said we should start by making a free body diagram, and I haven't been doing that yet just because I've been kind of focusing on how to find the work. So let's do this. All right, so here we go. So our force of gravity is going to be 10 times 9.8. It's negative 98 newtons. Our normal force, 98 newtons. So let's calculate the work done by gravity. So to calculate the work done by gravity, you're going to multiply the force of gravity, but I only want the component of the gravity that's parallel to the displacement. Okay? So now you want to make a drawing, and you're going to go, all right, well, my displacement vector is this way, my force vector is that way, they are perpendicular. So there's no component of this force if I split it up into components, there's never going to be a component that acts horizontally, okay? And as a result, this is just 0, because our parallel component is 0, times negative 20 meters, and so you get 0 joules, all right? The same thing is going to be true of the work done by the normal force, right? Because the normal force is up, and so by the same logic, you're going to get 0 times negative 20 meters, which gives you 0 joules, all right? Write this down in giant, super important letters. Any time the force is perpendicular to the displacement, the work done by that force is 0. That is super mega importante, enough that I'm going to draw a fancy, happy looking star. Hello, look how happy he is. He's got hands. Ah, creepy. Oh, and a hat. Okay, so let's see, what's next? All right, so this example I think is going to kind of tie everything together. What happens if the force is at a weird angle to the displacement? All right, so what I'm going to do here is I'm going to do an actual example where we're going to identify all of the forces acting on the object and calculate the work done by each of them. All right, so let's go back to this example here where let's have our box be at rest. All right, so we're going to go 10 kilograms. All right, Roy is going to push on it, but this time Roy is going to push at a weird angle. So let's say Roy, for some reason, decides to push this way. The force of Roy is, oh, I don't know. Let's go, I guess we can, will 50 newtons work? Sorry, I should have written up my example first. Okay, sorry about that. We're going to make the force of Roy 600 newtons. All right, and let's assume that that angle is exerted at an angle of 30 degrees below the horizontal. All right, and what we're going to do is we're going to make a free body diagram, and then we're going to calculate the work done by each of the individual forces. All right, so first thing we got to do is split up the force of Roy into components so we can make our drawing. So here's our force of Roy. We know this angle is 60 degrees. Sorry, I don't know if I said 60 before. I meant 60 before. 60 degrees below the horizontal. Sorry about that. So do your trig. The x component of this ends up being 300 newtons. And then the y component ends up being about 519 newtons. Okay? So let's go over here and make our free body diagram. All right, so here we go. 10 kilograms. All right, so step 1, force of gravity. Force of gravity is going to end up being negative 98 newtons. All right. Step 2, any given forces. So that's force of Roy. So remember, I'm going to replace the force of Roy with the two components. So here's our force of Roy in the x direction. It's 300 newtons. Here's our force of Roy in the y direction. It's negative 519 newtons. Let's see, we got to have a normal force, right? So if we've got gravity and Roy both pushing down, your normal force is the sum of those, which gives you 617 newtons. Please note this. I'm, at the time of recording this, just finishing grading a target check, and I'm still getting students making the normal force equal to gravity. And you can't do that, okay? So there's our normal force. All right, and then finally friction. All right, so let's suppose that there's a coefficient of friction here of, let's go with 0.2. Kinetic friction is 0.2. So that is going to make, our force of friction is going to be negative 123.4 newtons. Let's just go 123 newtons. I don't know why I went all that work to get rid of a decimal. Okay, so there we go. So there's our free body diagram. All right, having accomplished that, what we're going to do is now calculate the work done by each of the forces. All right, so let's do them in order. number one, let's calculate the work done by Roy. To do that, what I'm going to do is I'm going to multiply the force of Roy, but just the component that's parallel to the displacement, by the displacement. I haven't given you a displacement yet. Let's pick one. We've been using 20 meters, so let's stick with that. All right, so the displacement is forwards 20 meters, and I guess I implicitly implied, that's a bad sentence, that it was moving forwards when I made my friction backwards. Okay, so even though Roy's force originally was 600 newtons, here's the big idea, guys. Even though Roy's force was originally 600 newtons, the only part of that 600 newtons that is actually doing work is the horizontal component, because that's the component that is parallel to our displacement. All right, so I'm going to multiply 300 newtons by the displacement and discover that he did 6,000 joules of work. Okay, so that's the work done by Roy. All right. Number two, let's do friction now. Let's calculate the work done by friction. Okay, so to do that, what I need to know is I need to know how much force friction is exerting in a direction that is parallel to the displacement. Well, my displacement is horizontally to the right, and my friction is horizontal to the left. So they're already parallel, or I guess technically anti-parallel, so I can just multiply. So I'm going to go negative 123 newtons times my displacement of 20 meters, and that gives you 2,460 joules. Don't forget the negative sign, right? Because friction is working against the displacement. All right, so that's two of my three forces, or two of my four forces. All right, and then the last two forces are gravity and normal force, right? Well, both gravity and normal force are perpendicular to the motion. So for number three, the work done by gravity, well, I need my FG parallel times my displacement. Well, FG parallel in this example is 0, right? Because there's no horizontal force. So you get 0 times 20 gives you 0. All right, and similarly, our normal force is also going to be 0. So the work done by the normal force is also 0 by the same logic. Okay? So that's that. That is how you calculate work. And I believe that that example there hits all of the possibilities. All right, just as a heads up, there will be a problem on your homework where it's an inclined plane. You're going to treat it the exact same way. All right, you're going to, here's your inclined plane. You're going to take your force of gravity and split it up into components. So you're going to have a perpendicular component of gravity and a parallel component of gravity. Okay. So whether your box is moving up or down, the displacement is going to be in one of these two directions. So to calculate the work done by gravity, you're just going to multiply your FG parallel by your displacement. Okay. Once you've got this free body diagram done, you shouldn't really need this angle anymore. Okay. So there you go. Work.